Hello again. This is Math 2233 coming to you from the College page, and this is the conclusion of the lecture entitled Jacobians. As always, please be an active learner as you watch this video. At the conclusion of the previous lecture, we introduced this theorem, which I'm going to start this lecture with. So suppose T is a C1 transformation whose Jacobian is non-zero, and that T maps a region S in the UV plane onto a region R in the XY plane. Suppose that F is continuous on R and that R and S are either type 1 or type 2 plane regions. Suppose also that T is 1-to-1, meaning the inverse exists, except perhaps on the boundary of S. Then the double integral R f of xy dA is the same as the double integral over S f of x of uv, y of uv. This is the absolute value of the Jacobian xy/uv du dv. So this theorem says we can change an integral in x and y to an integral in u and v if it simplifies the integral. It also allows us to change a complicated region into a simpler region, or we can do both. And we do this simply by writing dA is equal to the absolute value of the Jacobian xy/uv, and this is du dv. So previously we showed that when we're using polar coordinates, dA is equal to r dr d theta. But this time I want you to use the theorem that we just quoted to show that dA is r dr d theta. You know what to do. Let's see how you did. So here's the transformation. We transfer region R into region S. This is r dr d theta. It is going to be what we want to come up with. So the transformation is x equal r cosine theta, y is equal to r sine theta. The Jacobian is this, and when I take the partials, I get these values. And then I take the determinant of those partials using this calculation, and since cosine squared theta plus sine squared theta is 1, this is r, and so dA is the absolute value of r is still r because it's bigger than or equal to 0. So get dA is equal to r dr d theta. Here's another example, and again we did this for using geometry before for spherical coordinates, but now we can use this theorem, and let's test this theorem out. So you should be able to show using this theorem that for spherical coordinates dv is equal to rho squared sine phi d rho d phi d theta. You know what to do. Let's see how you did. Okay, this is the transformation. X is equal to rho sine phi cosine theta, y is equal to rho sine phi sine theta, and z is equal to rho sine phi. So we set up this time it is a 3/3 determinant of the partial derivatives, and we go through and we calculate. Now this is a calculation that you should verify, but when you do this calculation of this determinant, you get minus rho squared sine phi. There are trig identities involved along the way and some algebra. But when you take the absolute value of this, the absolute value of minus rho squared sine phi, and note that phi was between 0 and pi for spherical coordinates. This ends up being rho squared sine phi d rho d phi d theta. Make sure you understand this example. Let's do another example. Let's use the change of variables, x equal u squared minus v squared, y equal to uv, to evaluate the double integral over r of y dA, where r is the region bounded by the x-axis and these parabolas. Y squared equals 4 minus 4x and y squared equals 4 plus 4x, for y being bigger than or equal to 0. You know what to do. Let's see how you did. Now this region that we have here, actually we studied in an earlier lecture. You might remember that we had these being R and S for that transformation. So that's the R that we're talking about. And if you look down here, if I just multiply both sides of this equation by 4, or both sides of this equation by 4, I get the parabolas that we have up here. So those are the identical parabolas. So the region that we had pictured is this one, and we discovered that T of S is equal to R. And so we turn that into a square, and that could be a good reason for making the change of variables, because that integral should be much simpler. So we will need the Jacobian. So if we take the Jacobian, we're taking the partial of x with respect to u, and the partial of x with respect to v, and so on and so forth, using these equations here. And we get this determinant, which we evaluate, and this is 4 u squared plus 4 v squared, which of course has to be greater than 0 because we're adding some square numbers together. So that means by our theorem that the double integral of r y dA is the same over this complicated region is the same as the integral over this simpler region of y is changed by this transformation up here to 2uv. This is the absolute value of that determinant dA, and that is a much simpler integral. We just have u and v going from 0 to 1. Y was 2uv, and we do have to put the absolute value of the Jacobian in there, and we put it in here. Now this time it's not a constant, but that's okay because we're integrating it. And so we compute this integral. I encourage you to follow all the calculations here, but we get an answer of 2. Now, it would have been a very difficult integral to evaluate if you didn't make this change, and so that is a demonstration, proof positive, that the Jacobian is very useful. Let's look at another problem. We're going to evaluate the integral over R, the double integral over region R of e to the x plus y all over all over x minus y dA. And R is the trapezoidal region with vertices 1, 0, 2, 0, 0, minus 2, and 0, minus 1. Now here we have a complicated function that might be simpler, and so we're motivating some change of variables there. And we also have a complicated region. You know what to do. Let's see how you did. Since it isn't easy to integrate this, we make a change of variable, and a logical change of variable is to call u equaling x plus y and v equaling x minus y. Now, these equations do define not only a transformation, but an inverse transformation. So we could solve these equations simultaneously for x and y, and we get x is equal to 1/2 parentheses u plus v, and y is 1/2 u minus v. You should verify this calculation. And so the Jacobian then associated with this is going to be, we take the partials, and here's the equations that we're taking the partials of, and it ends up being a numerical thing, but we get minus 1/2, and the absolute value of that is going to be 1/2. And to find the region S in the UV plane that corresponds to R, we note that the sides of R, down here, we have x minus 1 is equal to 1, and here we have x minus y is equal to 2. And so that means that whenever we do this substitution, we can have u going from minus v to v, and v going from 1 to 2, and that ends up being exactly the transformation for the regions as well. So the region S is the area, is the region we want. It is the trapezoid with these values. So with this substitution then, we're going to evaluate this. So using our theorem, the double integral over r of e to the x plus y over x minus y dA is the same integral over s e to the u over v. That was the absolute value of that is 1/2 du dv. And this then is going to be, we integrate first with respect to u, and then with respect to v. By the way, it would have been not easy to do, or in fact impossible to do, if we tried to integrate the other way, but we're doing it this way. So we go from minus v to v. That means we're fixing u. So we go, we're fixing v. So when we fix v, we go from minus v to v. So that's what we have. That is du. We integrate that, and now we have an integral that we can do. We substitute in. We do the calculations. Make sure you verify the calculations, and then we integrate with respect to v, and we get this number. This is the exact answer. Let's do another problem. Let R be the region bounded by the lines x minus 2y equals 0, x minus 2y equal minus 4, x plus y is equal to 4, and x plus y is equal to 1. And we want to evaluate the double integral over r of 3xy dA. Now notice that you have strong motivation for what to pick as your new variables. You know what to do. Let's see how you did. So certainly what you're going to do is you're going to let u equal one of these lines and v equal the other line, and then you're going to solve for x and y. And you should verify that this is in fact what you do get when you let u equal x plus y and v equal x minus 2y. Solving for x and y, you should get this. You make sure you know how to do that. But then the partial derivatives of x and y end up being these numbers, and I substitute them into the Jacobian matrix and do the calculation, and I get minus 1/3. That means there's a factor of 1/3, the absolute value that's going to go into the integral. So by our theorem that we have then, the double integral over r of 3xy dA becomes the double integral over s. Now s is going to be much simpler because it's going to end up being a square, or a rectangle, I guess I should say. So this is going to be 3. This is what x was. This is what y was. And this also is another factor of 1/3. dv du is the way we're doing that. And this is just an integrated integral. It goes from minus 4 to 0 and 1 to 4. You should verify this calculation, but at the end you get the exact answer of 164 over 9. Here's another problem for us to consider. Let R be the region bounded by the square. Now this is bounded by a square, so that's reasonably tame. But we want to evaluate the integral that looks like this. So it's the double integral over r. This is x plus y whole squared. This is sine squared x minus y dA. Some rather obvious simplifications arise from this. And in fact, we still haven't graphed this to see what this is. So you know what to do. Let's see how you did. Okay, this is what the R looks like, and you see it's lopsided, but you have a nice substitution that we're going to do. And when we invert, so we're going to let, x plus y is going to be one variable, x minus y is going to be the other. We're going to solve those for x and y, and doing that here, we get x is 1/2 u plus v, and y is 1/2 u minus v. We then take the partials with respect to u and v for x and y, put them into the Jacobian matrix, do the calculation, and we get minus 1/2 again. So by our theorem then, the double integral over r of the function in x and y dA is the integral over the new region, which is S, much simpler. And when I substitute those in, I get u squared sine squared v. The factor of 1/2 is in there. This is du dv. So I integrate first with respect to u, and then with respect to v. Now remember, when we integrate with respect to v, we have to use the double angle formula. But we do that, continue, and the 1/2 in the double angle formula came out here. And you should validate these calculations. We do term by term, and we substitute minus 1 and 1 in, and we get as a final answer 13/6 parentheses 2 minus sine 2. Now this is the sine of 2 radians, which is a number. This is the exact answer. If you plug this into a calculator and came up with approximation, we had this. Before we go to our last example, I'm going to mention that everything that we've done so far, the region S has been kind of a rectangular thing with sides either parallel to the U or V axis. Occasionally, changes of variables can be used for other types of regions. For example, we could talk about circular regions and ellipses. That's the kind of thing we're going to look at in our last example. Determine the new region that we get by applying the given transformation to the region R. So R is the ellipse, x squared plus y squared over 36 equal 1. And the transformation is x is u over 2, y is 3v. You know what to do. Let's see how you did. Well, we really could just substitute in. And when we substitute in, some nice things happen. And we end up that the algebra leads us to that the ellipse becomes something tamer. It becomes a disk. And the disk can be integrated using polar coordinates or otherwise. So you see, sometimes you can use these kind of substitutions to, in fact, simplify a region so the integral is easier to do. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. We're all in this together. May God bless you all.